Welcome to the session on energy transport as part of NPTEL MOOC on transport phenomena and materials. This topic is also referred to as heat transfer in most of the courses. So, in this course we are going to take up heat transfer after the fluid flow sessions, mainly because there is a strong linkage between these two phenomena. And in this session we are going to look at the enthalpy change from the thermodynamic principles and argue the spontaneity of heat transport and then motivate the linear constitutive relationship which we will be using here, and then derive the generalized heat conduction equation which will be the governing equation for heat transfer, and then we will introduce the concept of heat transfer coefficient, boundary conditions and problem statements. That would basically be the starting point for us to solve some of the problems on heat transfer that we encounter in metallurgical phenomena. So, the enthalpy change is going to be discussed motivated from the first law of thermodynamics, where we write the change in the internal energy as written here, which is basically the difference in the amount of heat that has come in and the work that is done by the system. So, we write, for example, the differences with a different symbol here delta, because these two are path functions, whereas here we write with the d indicating that it is a state function. Okay. And we restrict the work to be the PDV work, so that we will later on look at the constant volume and constant pressure situations and see whether these terms will survive or not. We can also take the chemical work, but at this moment we are not going to take those into account. The enthalpy as a thermodynamic function is defined here. So, we write this with a triple equal to sign, because this is actually the definition, and once we write, then we can actually look at the change in the enthalpy as related to the change in the internal energy and the rest of the parameters. So, we write by straight away taking the differentiation by parts for the P and V. So, once we write this, we basically combine this equation with the first law and realize that we can express the change in the enthalpy to the amount of heat that has come into the system, and at constant pressure we see that the second term will drop. So, this is exactly the idea. Most of the engineering situations the pressure is actually kept at 1 bar, and very often we also are using the condensed systems, that is liquids and solids, where the pressure effects are very minimal. So, therefore, most of our discussion will be with the heat transfer at constant pressure. So, once we write, then we can also see how the change in the enthalpy can be expressed further on. So, here we are proposing that the enthalpy can be written as a function of temperature and pressure. So, for any function that is a function of two variables, you can actually write what would be called as an exact differential. So, this is actually a mathematical concept saying that the differential of enthalpy, if it is written as a function of temperature and pressure, can be expressed in terms of the partial derivatives and the differences of respective variables. Now, if this is so, then what we can do is that compare this equation with the one that we have derived. So, this equation when we compare, then we can already see that this term would be here comparable, and then we could also see how we can express the amount of heat that has come into the system to raise the temperature by a small amount. Okay. So, then we can give some name for this particular quantity, and that is how we are actually introducing. So, we basically call that as the heat capacity, and per unit weight or per unit volume or molar heat capacity etc., is depending upon the variable that is in front of it. So, this is how we define, but remember that it is all valid when we are taking the pressure to be constant. So, basically motivated from the enthalpy, we basically say that the amount of heat that has come into the system is actually leading to directly a change in the enthalpy, and that can be related to the temperature change via the heat capacity. So, once this is there, then we can see how this actually applicable for most of our systems. So, if you take many of the materials, pure materials, for example, if you take pure iron and then the melting point is indicated here. So, as you increase the temperature at the melting point, there is a certain amount of heat that has to be given to break all the bonds between the atoms in the solid state to make them into a liquid state. So, here we have got the solid state here, and this is the liquid state, okay. And this is also called as the latent heat of fusion. or enthalpy of melting and so on. Okay. And you could see that this actually makes the expression for enthalpy a little complicated because there are changes of slopes, but as long as you are not changing the phase, that is if you are sticking into only the solids or the liquids, then you can have a direct proportionality relationship between the enthalpy and the temperature. And the enthalpy change as you go along this curve is given by the integration that is written here. So, you could apply this either in the solid state or in the liquid state, but when you do across, then you also need to look at the latent heat of fusion without forgetting, because that is an addition that will come because of the change of the phase. So, assuming that there is no phase change, okay, assuming that you do not have a phase change, then you can straight away use this straight line approximation and write that the enthalpy is related to the differences in the temperature, where the slope is nothing but MCP. Okay. And if you were to then also apply it for a given domain, then we know that the mass of the entire domain depends upon the geometry. And in transport phenomena, we have been generally using the control volume approach, so that we write the expressions for a given control volume and then we just integrate for the whole volume depending upon the geometry, then the integration can give you the results. So, we do not want to write the quantities for a entire body, but actually for a control volume. So, we write the enthalpy per unit volume here divided by the volume, and you can see I am using a small h to say that it is enthalpy per unit volume. So, you have rho Cp into the delta T. Now, the T reference is basically some reference point to indicate the scale of the enthalpy to start at 0, and usually you take it as a 298 Kelvin as a reference. So, you could also take it as any other reference, but remember that it is always the differences of enthalpies that we are interested in very often. And from here you can already motivate that for any given body, because if you integrate the density over the entire volume, you get the mass. So, you can already motivate that the enthalpy change is nothing but integral of the enthalpy per unit volume over the entire volume. So, once that is there, then we will actually use that concept later on to derive some of the expressions. So, here we bring about what we mean by thermal equilibrium, because heat transfer is basically a tendency of the system to go towards thermal equilibrium. And we say that there are two bodies here, 1 and 2, and these are at two different temperatures T1 and T2. And if they are actually at thermal equilibrium, what we want to then conclude is that T1 should be equal to T2. Okay. So, which means that the measure of the equilibrium is basically given by the temperatures. So, that is how we want to define the thermal equilibrium as. And if we now take two bodies that are at two temperatures T1 and T2, and if they are different and if they were to reach the equilibrium over a period of time. Okay. So, initially T1 is not equal to T2 and later on they reach an equilibrium, and if these two bodies are identical, okay, there are two identical bodies, they have the same amount of mass and their contact is perfect contact. So, we say that the contact is perfect, so that there is a good amount of heat that can go across to make the equilibrium be achieved. And if that is so, then we can already see that the average temperature that will be seen in both of these bodies is given by T1 plus T2 by 2. This actually makes us that the intuition that the heat actually is going in this case, for example, if you were to tell that T1 is a low temperature and T2 is a high temperature. So, we say that the heat is going this way, so that the T2 is reduced to T bar and T1 is actually increased to T bar, where T bar is basically the average of T1 and T2. Now, this actually makes us come to a conclusion that heat is actually going from a location of high temperature to low temperature, and I want to just quickly remind you why we would like to call this as a spontaneous process. So, here is where we remember something from thermodynamics. Any process that increases the entropy would be spontaneous. So, if in this process of temperatures being equilibrated, if the entropy were to become positive, that means it is a spontaneous process. Through that we basically discover the cause and effect relationship, which we then use for the linear constitutive equation that we need for heat transfer. So, you write the entropy change for the entire body in this manner. So, you say that the entropy change for the first body is delta S1 and for the second body is delta S2. This is going from T1 to T bar, this is going from T2 to T bar, and you could write the delta S is basically integral ds, and that we write as delta Q by T, and we already know that delta Q is given by, for example, mCp into dt. So, therefore, we can write here the delta S as mCp dt by T, and if you want to go from T1 to T bar, then you could write it as mCp logarithm T evaluated between the limits T and T bar, and that would be mCp log T bar by T1. Okay. Similarly, you can then see how you could write it for the other expression also. So, you then see that it is coming here. Similarly, it is also evaluated for the second term, and then you can get the sum of the two entropies like this. Now, when is this process spontaneous? The process is spontaneous when the total entropy change is greater than or equal to 0. So, that is when it is spontaneous. So, we inspect whether it is spontaneous or not by looking at only this term, because these are actually anyway multiplicative factors, and if this term that I am highlighting, if that is greater than 1, then what happens? The logarithm of a quantity more than 1 will give you positive number, and therefore, the entropy change will be positive. If this number happens to be less than 1, that means it will give you a negative number when you take logarithm, and then the entropy change will be negative, which means that the process is not spontaneous. So, we will only look at this term, and to evaluate whether the term is positive or not, you look at the expression here. So, as long as the T1 and T2 are two temperatures, if they are different, you know that whether the T2 is more than T1 or less than T1, the difference square is always positive, okay, and therefore, we say that it is greater than or equal to 0, because T1 and T2 are equal, then you get 0 there, and you expand T1 minus T2 square, and then take the 2 T1 T2 to the other side, and then add 2 T1 T2 to both sides, then you see that you can write this expression. Once we write this expression, you take this 4 T1 T2 to the denominator, and then you can write that the entire expression is greater than or equal to 1, which means that the logarithm of that is greater than or equal to 0, which actually means that the entropy change for this entire system is given as greater than or equal to 0. So, which also means that in the process that T1 went up to T bar, and in the process that T2 went down to T bar, it is actually that entropy change total is actually greater than 0, which implies this is actually a spontaneous process. And in this process, what is happening is that the heat is actually going down this direction. Okay. So, heat going down the temperature gradient is a spontaneous process. Okay. That is exactly what is our conclusion from here, which means that we are now able to propose a constitutive relationship where we can talk about the cause and effect relationship. If the cause is the temperature gradient, then the result will be the heat flow, and the sense of it is that the heat will be flowing down the temperature gradient, and that is exactly what we are writing here. We are saying that here J is the heat flow, okay. So, in per unit area, okay, heat flux, and this is the temperature gradient. So, we want to use this minus symbol, we should say down the gradient. Okay. So, we are saying that the heat flux is down the temperature gradient, and then if you want to look at these two as vectors, and they should be related by a property, and from the tensor relationships that we have discussed earlier in the beginning of this course, we know that the highest tensorial order for the property that can relate these two vectors would be a tensor of order 2, and that is exactly what we also want to call as thermal conductivity tensor, which is of order 2. Okay. So, that is what we can conclude here, and we have seen this linear constitutive relationship actually come out with a name, Fourier heat conduction, where the heat flux is given as proportional to the temperature gradient, where the proportionality constant is k. Now, normally k is taken as a constant, but we know that the most general form of writing this relationship is where k is actually a tensor of order 2. K is actually a symmetric one also, as we have discussed earlier. This is because of the Onsager's principle. Okay. So, Kij is a symmetric tensor. So, we will look at problems where k is actually a tensor of order 2 with 9 components reducing to 6 because of symmetry, and for different crystal symmetries how different values of k are required. So, we will take that discussion separately and see how we can actually write this expression for isotropic materials. So, for isotropic materials k is just one number and that we have written here, and in the rectangular coordinate system you could write the heat flux related to the thermal conductivity in this manner, where we have written the gradient. So, the gradient is written here in the rectangular coordinate system, and if it is cylindrical you can write it with respect to the r, theta and z components of the gradient, and you can see that it is written here. And for spherical coordinates, of course, you write it for r, theta and phi directions, the variation of temperature in those directions, and we can write the temperature gradient like this. So, temperature gradient into the thermal conductivity with a minus sign is giving you the heat flux, and that is what is basically called as a Fourier heat conduction. Okay. So, in the realm of most of the engineering scenarios, we normally encounter only Fourier heat conduction, because the non-Fourier heat conduction is out of the purview for our course. It normally happens when we have laser pulsing at time scales that are very small, like picosecond or so, but most of the engineering problems where the heating is done at the expected rates and pulsing is done in milliseconds or so, or even more, then Fourier conduction equation is valid, and that is what is written here. Now, we need to have a governing equation derived. So, the template for governing equation is exactly the same as what we have done for the Navier-Stokes equation, and that is given as follows. So, we start off with a balance equation. So, for Navier-Stokes equation we start by the balance of the linear momentum. So, in this case for heat transfer we start with the balance of heat or balance of energy. So, we start with the balance equation, and then we apply this equation for a control volume. So, we write mathematically for a control volume, and then normally when you write it for a volume you would have the bulk terms, the volumetric terms as well as the surface terms. So, the surface terms are going to be then converted to the bulk terms by using the divergence theorem, and then once you have that written, then you would actually look at only the integrands and then change it by using a constitutive relationship, so that the cause and effect relationship is used, and finally we have the governing equation. So, this template will be applicable for all the transport phenomena, and usually if you follow this we are also very conscious of what is our starting point. So, it is the balance of enthalpy that is the basis for heat transfer governing equation. So, that is something that we have to be very clear, because that is the starting point for us. So, what we do is first we state the balance. So, balance is stated as follows. So, the rate of increase of enthalpy in a control volume is because of heat generation that is done volumetrically in the control volume and the influx of heat from all the faces. So, if the heat is coming in and also there is a heat that is generated, so therefore, then it should lead to the increase in the enthalpy of that particular control volume. Enthalpy being a thermodynamic function is anyway related to temperature. So, we would see that it eventually leads to increase in temperature, but the balance is written for enthalpy. So, we would write that, okay, and we write it now in mathematical form for a control volume, and we are then very consciously using the Eulerian frame of reference, which we have discussed in detail in an earlier session, where we use a material derivative to look at the rate of change. So, rate of change with respect to the time is used with capital D, which is a material derivative. The reason being that this is for a control volume which could be in a fluid also, and in a fluid when you go whatever is the function that you want to write. So, this entire thing for example is a quantity, let us say capital phi, then capital phi at any time, okay, limit delta t goes to 0. So, this is what we actually mean when you look at this quantity. Now, here we see that at t plus delta t is the control volume elsewhere compared to here. Okay. So, the reason being that there is a velocity that is actually present and the control volume will actually move around. So, then if you use the fact that you could actually use the chain rule of differentiation, then you would actually get the velocities also, and that is what we discussed when we came about the material derivative. So, please refresh that concept before we continue further, and then we will be able to write the rate of change of enthalpy as material derivative of this integral, and this integral what is there is basically the enthalpy of the entire control volume, okay, and that is equal to the volumetric heat generation. So, G is the rate of generation of heat. So, rate of heat generation per unit volume, that is written as G, and that would be basically watt per meter cube, and then the influx of heat. So, the influx of heat we always write with a minus sign. The reason is as follows: the J is actually by our convention is a outward vector, okay, and when it is dotted with the surface normal of any phase, that is also outward. So, when you dot it, you get a quantity that is positive if the flux of any quantity J that is represented is going out of the control volume. So, you must actually then put a minus sign to indicate that we actually saw about the inward flux. So, that is why we say that if this is the amount of heat that is going out of the phase that is indicated here, then with a minus sign, that actually then represents the influx. So, what we have written in this particular equation is that it is a mathematical form of whatever we have said here. So, this is actually this. Okay. So, these two are identical, one is in English and other is in the mathematical expression. Now, what we do is that we then go on to manipulate this expression further on to arrive at the governing equation. So, that we do as follows. So, we write the same expression here H, but H is then written with respect to the expression that we have already seen. It is rho into Cp into T minus T reference. Okay. So, that is what we write here, okay, and integrated over dV, that will give you the enthalpy, and then the rate of change of enthalpy is indicated by this, and that is equal to the integral of the rate of heat generation volumetrically and the influx. Okay. So, we wrote that again neatly by expanding the small h, and then we see that it is a bit awkward because there is a differential here outside of the integral and the rest of them are actually integrals. So, we must take that in, and what enables that possible is the Reynolds transport theorem, which again has been discussed earlier, and we know that it can be taken in at that position by this Reynolds transport theorem for any arbitrary scalar function, and luckily for us temperature is a scalar function, and therefore, we can directly do that. And here we have basically integration which is over the entire surface of the control volume, and if we want to then change it to the volumetric integral, then we must apply the divergence theorem. So, divergence theorem is over this index I. So, this basically whatever you have written is J dot ds, and we know that that can be converted to del dot J dV integral over the volume, okay, and this is what actually we apply. Okay. So, we have then taken the d by dt material derivative inside, here it has come in, and we are actually converting the surface integral into a volume integral here by taking the divergence. Once we write, then we recognize that all these three terms are actually having the integration over the same domain, namely the volume of the control volume, and therefore, if this equation were to be true, then it also means that the integrands are also equal. So, whatever I am highlighting, that is all the integrands, and they must also be following the same expression. So, that we then indicate here. Okay. So, which means that we now have expressed the balance of enthalpy without using the integrations by writing it for the control volume and then adjusting the term such that everything is over the same integration. So, we now have basically a governing equation for the enthalpy balance, but we still need to do some more, because here we write J, which is the heat flux, which needs to be converted into the temperature differences, and that we do basically by using the linear constitutive relationship. But before we proceed, we just let us look at the operator d by dt material derivative that we have already come across, that is expanded here. So, we expand the material derivative here, and if you then want to consider that this is constant, okay, which means that it is not a location dependent quantity, then you can take it out. What it means is that in problems where you have location dependent properties, then do not do this manipulation, you can use the equation as it is, but in case of homogeneous media, then you can take the location dependent properties. If they are not relevant, then you can take this guy out, okay, and then you can collect the properties aside and then look at that the material derivative is acting only on the temperature. Okay. So, this entire thing is basically d by dt of the temperature, material derivative of the temperature, that is all, and that is equal to basically G, which is the rate of heat generation volumetrically, and the divergence of the flux. Okay. So, we then write this expression in vectorial form saying that material derivative of temperature with a property is equal to the rate of heat generation and the total influx, which is given by the divergence of the flux. Now, the flux is then expanded, okay, and we expand the flux in this manner, okay, where we basically already have talked about it. It is basically the Fourier conduction, okay, Fourier heat conduction equation. The flux is equal to minus k into the del T, and k, for example, here is a tensor of order 2. Then we want to make a simplification that for isotropic materials we want to consider it as an isotropic tensor, and therefore, we can write it as k into del ij. So, look at this expression. Okay, so, you look at only this expression. If you write k del ij and then dou T by dou xj, then we know the principle that whenever the Kronecker delta is coming, for the matching index you can then manipulate, and then this can be written as k dou T by dou xi. So, this is what we have written, and that goes here. Okay, so, this comes straight away here. Okay, so, rest of it is here. So, which means that we can actually look at the last term and recognize that it can be written as k into del square T. So, which is basically Laplacian that is coming in, okay. And on the left hand side we have basically the rho Cp, and then this is the material derivative, okay. So, we can see that upon introducing the Fourier heat conduction equation, the minus sign is actually taking care, and you have got a plus sign here because you have got 2 minuses here, these two getting cancelled out, okay. So, we now have the governing equation for heat transfer. So, we write it in a different manner. So, we already see that the properties are being assumed constant. So, constant thermal conductivity, etc. So, we can then take it to the right hand side and write it as follows. So, when you take it to the right hand side, k by rho Cp comes, and k by rho Cp can then be called as the thermal diffusivity, which has the units meter square per second, and we already saw some quantity of this nature new in the mass transfer also earlier. The momentum transfer, we look at what is called as the momentum diffusivity, and that is basically new, okay, kinematic viscosity, and that has also the same units, okay. So, we then substitute that here, and g by rho Cp comes about because rho Cp is taken to the right hand side. So, now this is basically the governing equation for the heat transfer for us, okay, with the advective term and the partial derivative with the time, all of it coming because of the material derivative on the left hand side. So, this first term goes by the name transient term, and the second term goes by the name advective term. These two together are coming because of the material derivative, and that is because we have used Eulerian specification, okay. And this term is called the diffusive term because it basically tells how the temperature variations are getting evened out, okay. We will see the result of that shortly when we solve some problems, and G is basically volumetric heat generation term, and therefore, that is called as the source term. So, we can see that the terms are very similar to that of the Navier-Stokes equation. We do have a transient term, we have advective term, we have a diffusive term, we have also source term. The only thing that was missing is in the Navier-Stokes equation you have the pressure gradient term, which is not relevant in heat transfer, but otherwise the 4 terms are there. And the way the terms actually interact on the equation to get you the solutions of different types is also similar, and so some of the solutions can already be guessed by looking at what kind of solutions are possible if the equation looks like this. This equation has another name. You could also call it as the so called convective diffusive equation, okay. And this basically means that these two terms are being taken into account, and so in mathematical literature sometimes what people refer to as convective diffusive equation is nothing but this generalized equation that we have written, which falls into a template into which the Navier-Stokes equation or the generalized heat transfer equation also can be cast. So, it is a very broad template that is widely used, okay. So, the Fourier heat conduction we now then expand. So, what we do is this equation we expand. So, we expand these terms in different coordinate systems. So, for rectangular coordinate system we expand the advective term. We can immediately see that this can then be expanded here, okay, and del square can be expanded here. Okay. So, this is the first and this is the second, first operator and second operator. So, we can see that the most general form of the Fourier heat conduction equation in rectangular cone system will have, for example, these many terms, and you would see that the velocities are directly coming here, and you have got the diffusion term on the right hand side. And the same thing can be also written for cylindrical cone system, where the velocities are actually u r, u theta and u z, and you would also have the Laplacian looking a bit different. So, watch out the Laplacian term different for this system. Okay. So, you can see first of all here. Okay. So, the r into dou t by dou r 1 by r here. So, this is a very important difference that you need to note down, but in the z direction by and large it looks the same. Okay. So, we can look up these operators for different coordinate systems and substitute, which means that if you knew how this has come about, and that is adequate. So, from here to here you could basically look up the operators and substitute and figure it out. So, that is adequate. And we have written this equation for isotropic materials. Why do we say that? Because here we are taking it as a constant, and this is nothing but k by rho Cp, and k is constant, and that is because we are taking about for isotropic materials. And why do we say it is for constant properties? That is because we have already collated these constants k and rho Cp we have taken from the left hand side and taken it under this. So, which means that it is only applicable when the properties are not spatial coordinate dependent. So, that is also an assumption that we have written. Okay. And for spherical coordinate systems, so the equation looks like this. So, you have got u r, u theta and u phi coming in, and the Laplacian term for spherical coordinate system is looking like this. Notice that the power of r is different from the cylindrical coordinate system. In cylindrical it is r, and here for spherical it is r square that is coming in. Okay. So, other than that you can actually look up these from a handbook and substitute directly. Okay. And these are going to affect the heat transfer in the following manner. So, you could see that you have got the temperature and also you have got the velocity. So, how does the fluid flow affect the heat transfer and vice versa? So, that is a concept, and we are not going to go in depth because we would have coupled problems being solved later on, but at this point I would mention that the fluid flow is going to affect, we would say that the fluid flow is going to affect the heat transfer mainly via the advective term. So, this is how mainly it will happen. Okay. So, the advective term is already visible here. So, this is advective term. Okay. So, advective term is what is going to cause an effect of the fluid flow on the heat transfer. But there is also another way by which it can affect, and that is through viscous dissipation. That is because when the velocity gradients are very steep, and that would lead to basically release of heat, and that would also be affected, and that would come by the G term. Okay. So, this term is coming from viscous dissipation. It is possible. So, in situations where there is a very narrow gap of liquid, for example, in lubrication situations, the velocity gradients are very steep and viscous dissipation can be quite high, and that also can lead to heat transfer. So, the way fluid flow affects heat transfer is by mainly by advection term, and sometimes when steep gradients are present also by viscous dissipation. Now, how does heat transfer affect the fluid flow? That would actually affect via the properties. So, you could see that it is actually affected via the temperature dependent properties. Okay. So, if you have, for example, rho that is dependent on temperatures, so then it will lead to what is called buoyancy flow, and if you had, for example, surface tension that is dependent on the temperature, you would have what is called the Marangoni fluid flow, etc. So, like that heat transfer can lead to fluid flow, and fluid flow can lead to heat transfer, and in such a coupled situation how do we go about? So, we do it step by step, we take one at a time, and at this juncture we basically take heat transfer alone and avoiding the advection term, and that is when we write the equation for solids. So, we write for solids, isotropic solids, how the equation should look like. So, on the left hand side you could see that we have dropped the advective term mainly because the velocities are 0. So, the Fourier heat conduction equation for solids is appearing to be very simple, and this if you write it in the way that normally seen in the books, you could write it in this fashion. So, it is as small as this. So, you are actually expanding the Laplacian here in this equation, and in cylindrical coordinate system it is expanded here and the Laplacian is actually here, okay, and in spherical coordinate system similarly it has been expanded. So, for Fourier heat conduction in solids which are isotropic, then you can see that the equation is quite small and that can be solved. Now, what kind of simple solutions are possible? So, this is something that we need to inspect, because upfront we can actually already get some insight of how the heat transfer is taking place. So, consider these equations and look at the simplest situation possible when, for example, you are looking at steady state. So, you do not want to look at that, and we say 1D. So, you do not want to look at variation in other dimensions, and without heat generation you do not want to have this term, which means that you have only one term that is set as 0, and what kind of solutions are possible. And you can already see that this kind of a equation would give you a line as a solution. So, we could see immediately that straight lines are valid solutions of temperature under one dimensional steady state heat flow without heat generation. So, mx plus b, okay, ax plus b is definitely one of the solutions that is possible. However, when we go to cylindrical coordinate system, the same thing when you apply to, for example, here, then it will be logarithmic variation, and in spherical coordinate system when you look at this term you would see 1 by r variation. So, you could already see that steady state heat flow in 1D without heat generation can appear to be straight lines or logarithms or 1 by r's, okay, all of these are valid solutions. So, we can then imagine how the temperature profile would look like in a given problem, draw some schematics and thereby evaluate how the entire thermal profile should look like, so that it will help us in posing the problem properly. Okay. Now, here is where actually all these three coordinate systems are going to be useful in metallurgical scenarios. So, in metallurgy we have heat treatment that is happening for many components, and that is one problem where the heat transfer is directly used in solid state. And so, we have basically the furnaces where the heat treatment is being done. So, we do have what are called box furnaces, tube furnaces and muffle furnaces or even pit furnaces. So, normally box furnaces can be modeled using rectangular coordinate system, tube furnaces can be modeled using cylindrical coordinate systems, muffle furnaces or pit furnaces where the sample is very small compared to the volume of the heating zone that is around it, then you can actually consider it as a spherical coordinate system. So, we have scenarios of all these three coming up in metallurgy, which means that ability to solve heat conduction equations in rectangular, cylindrical and spherical coordinate system is something that all metallurgical engineering students should be able to possess. Okay. Now, when we solve these problems we have to pose the boundary conditions, because that would only make the problem unique or a well posed problem. So, there are many boundary conditions that we can write. The first boundary condition we come across goes by a name Neumann boundary. So, Neumann boundary condition is where the heat flux is specified at the boundary. So, the heat flux is given already by the Fourier's heat conduction equation here, and we are evaluating at S, which means that it is evaluated at the surface or the boundary. Okay. So, the heat flux that is evaluated at the boundary is given as a constant. So, J naught is basically a number. Okay. So, once you have the heat flux as a number, then that means that you are actually using what is called as a Neumann boundary condition. So, sometimes you may say that the surface is insulated. So, there is no heat that is getting in or getting out. So, in such situations you can use what is called as a no flux boundary, which is a special case of Neumann boundary condition where J naught is 0. So, when J naught is 0 you can drop K and you can say that the temperature profile would have a maximum or 0 slope at the surface, and that would be a no flux boundary condition. And Dirichlet boundary condition is when the temperature is specified, the value of the parameter is specified, not the slope. Okay. The slope is specified, is called Neumann boundary condition. If the value is specified, it is called Dirichlet boundary condition. So, if the temperature at the boundary is specified, it is called the Dirichlet boundary condition, which is also quite popular. So, usually these are very popular because you can achieve the insulation to give this. This is actually requiring some task because you need temperature controls. Okay. And therefore, these are not very easy to achieve. These are actually also easy to achieve because you actually have external heat sources that can give heat flux at a particular rate to the body. Okay. So, if you have metallurgical scenarios, usually you would be encountering any of these things coming in as boundary conditions. So, we must inspect the problem and see which boundary condition is suitable at which location of our domain. And we also have very often the flux condition not specified as a constant, but as a function of temperature, and very common boundary condition like that is a radiative boundary condition. So, bodies that are exposed to radiation from outside or which are losing heat because of radiation can be basically specified as a flux at the boundary losing heat by radiation given by Stefan-Boltzmann law, and that means that the flux at the boundary, okay, S indicates that at the surface is specified by the heat loss by radiation. So, the fourth power should tell you that it is a radiation equation. So, this is Stefan-Boltzmann constant, and this so sigma SB is Stefan-Boltzmann constant, epsilon is emissivity, and F12 is basically called as the view factor, which is indicating whether the radiation is actually able to go away or is it being shadowed, etc. And normally radiation is treated not as a heat transfer mode within the domain, but only as a boundary condition. So, the reason is as follows: most of our metallurgical problems involve the domain to be either solid or liquid, and when you have solid or liquid, then they will attenuate electromagnetic radiation given by the Beer-Lambert's law here, that is given. Now, that is exponentially the intensity of the radiation going through the condensed matter is going to go down as e raised to the power of minus mz. This m, okay, m depends on the density of absorbing particles or atoms, which means that it is proportional to the density of the material, which means that in gases you would have radiation going to the complete domain, but if the domain is made of not gas but solid or liquid, then within a short distance, because m is proportional to density which is very high for the solid or liquid, m being very large means that the Iz will be 0 very soon, which means that the radiation is going to be absorbed only within first few microns of the body, which means that mainly is a boundary condition. So, that is the reason why radiation is treated as only a boundary condition in metallurgical problems. Of course, if you are going to model a furnace, the interior of a furnace, then it is not true, but most of the time we are actually having the domain not as a furnace, but the sample that is inside the furnace, and therefore, this kind of a thing is applicable. So, radiation is only a boundary condition. Okay, so, here is where we want to then look at what happens for boundaries where you have got a fluid in contact. Okay. So, what happens is that when there is a fluid, and if you are going to look at hot body in contact with a cold fluid, then you know that far away in the fluid the temperature is low. So, you can see here the temperature is low, and this is at T infinity, and the interface is at T s, that is given here. So, we see that the temperature may fall in this manner. Okay. The reason why we draw it parallel to the axis far away is because the interface is far away, and so the heat loss is not felt very much away from the interface. So, which means that the temperature profile has to be drawn in this manner, okay, asymptotically going towards T infinity whenever a hot body is in contact with cold fluid. If it is a cold body in contact with a hot fluid, we actually also make it as a asymptotic, but going to a high value. So, asymptotic manner is always drawn, and this kind of a heat transfer would indicate, for example, in this case the heat transfer is going in this direction, in this case heat transfer is going in this direction. So, in these kind of a situations, it is very difficult to ascertain what will be the slope of these variations. Okay. So, the reason being that they depend upon the fluid flow. Okay. So, if you have the liquid that is convecting, then it would change the slope, and very difficult to find out what will be the slope here. So, because of that, what we do is that instead of expressing the heat flux at this interface as a slope, what we do is we just take the difference of the temperatures and then express, and that is where we actually come across the definition of heat transfer coefficient. So, we say that in boundary conditions you may also have a situation where you want to call it as a Newton's law of cooling, and the heat flux at the boundary, which is given by x is equal to 0, is written as h into T s minus T infinity. So, difference of temperatures into h. And we also need to remember that h is always defined to be positive, which means that from this expression you can immediately see that h is defined with an absolute magnitude of this particular quantity, that is flux you take it, whether it is positive or negative, whether it is going towards the left side or right side, take the magnitude, divide with the temperature difference, and that will be giving you the heat transfer coefficient. So, H is what we now define as heat transfer coefficient, okay, which is watt per meter square. Okay, so, heat transfer coefficient is then defined once here. So, we should not confuse that to be a physical property. The reason being that it depends not only on the thermal conductivity of the fluid that is in contact with the solid body, it also depends upon the velocities that are there in the liquid, the geometrical structure of the interface and so on. So, therefore, it is basically a dump factor. So, you can think of it as a dump factor whenever there is a boundary in contact with a moving fluid. So, the fluid property like thermal conductivity plays a role. So, if you have a fluid that is have a higher thermal conductivity, then H will be higher and so on. It is also very often used to model what is called contact resistance or interface resistance. What we mean by that is as follows: if you have two bodies, then if their contact is not perfect, if you were to then zoom in here, so you see that between them there is an air gap, okay, and this is a solid 2 and this is solid 1. So, which means that the temperature profile across this body, for example, could be like this, which means that the temperatures at these two ends will be different, okay, which means that the heat flow this way should be dependent also on this gap, and this air gap is what is causing the contact resistance, and very often this air gap is a function of the surface roughness, etc., which is very difficult for us to model. So, the entire thing can be dumped and say that this leads to a H which is at the interface. So, heat transfer coefficient can also be used at interfaces where there is a contact resistance that is present, and for situations like spot welding, resistance spot welding, this plays a very big role. You also can use this concept to do what is called linearization. So, in radiative heat flux you can also use it for linearization. So, you could look at this, for example, epsilon into sigma into T raised to the power of 4 minus T infinity raised to the power of 4. Now, this is a fourth power law, and if you want to then convert it into a linearized equation, you could write it in this manner: T square plus T infinity square into T plus T infinity and then T minus T infinity. So, you could see that these both are equivalent, and then this entire thing can be written as H effective into T minus T infinity. So, you could actually linearize a fourth power equation into the heat transfer coefficient kind of a scenario, where the effective heat transfer coefficient can be given as epsilon sigma into T square plus T infinity square into T plus T infinity. So, that way we can actually linearize using this. So, H can be used for multiple purposes. It can be used for linearization, it can be used to model the air gaps, contact resistance, and it can also be used as a dump factor whenever there is a fluid with unknown fluid flow that is taking place. Okay. And we need to then now move on to make couple of problem statements. So, we will do it only for 2 domains and 2 situations, and then the problem becomes well defined, and therefore, we can start to solve the equations. So, this is the generalized heat conduction equation we have written for the domain which will have solid and liquid, etc. So, we have the advective term, we have the the transient term, the advective term, the diffusive term, and the source term that are present. So, we make statements about the problem to make it a little more well defined. So, if we say that the problem is under steady state heat transfer. So, the moment we say steady state, that means we drop this, okay, and make that because of the assumption 1, okay, and we say that let us say it is for solid domain. Okay. So, the moment we say solid domain, you know that U1 and U2 and U3 are all 0. So, the entire thing can be dropped, and this is because it is a solid domain. Okay. Then we say unidirectional heat flow. So, we let us say in x1 direction, which means that along the x2 and x3 directions there is no variation of temperature. So, we can then use that to drop these. So, as per the assumption 2, we can drop those, and if you say that no heat generation, that means we can drop this. Okay. So, like this we can actually drop terms depending upon the problem. It is not necessary that all these assumptions should be there in a given problem, but we should look out when are these assumptions applicable, and accordingly reduce the number of terms in the equation to help us integrate and arrive at the solution. Sometimes we may also have situations like this, constant power loss. Okay. So, which means that you may have situation like J can be thought of as Q by area, and Q is then given as a constant. and J is already written, we know that K into grad T. So, you can think of that, this means that minus K into area into grad T is constant. So, this can be an assumption also that can be given, which can also simplify the problems. So, we can actually reduce the number of terms depending upon any of these assumptions. We can also make these problem statements for liquid domain. So, for liquid domains, you already see that these things should be present, and that is because advective term is present. Okay. Now, steady state would mean that you could drop this. So, first term can go. Plug flow, by plug flow we mean constant and unidirectional velocity, which means that say u1 is equal to constant. Okay. So, which means that you can drop u2 and u3 if it is a plug flow. Okay. Plug flow along x1 direction would mean this is a constant and u2 and u3 has 0. Okay. So, you could think of that. In case if it is written as unidirectional steady flow, you could also think, if it is third assumption, then u1 could be a function of x2 for example, that is allowed, but u2 and u3 will be 0 in case the unidirectionality of flow is along x1 direction. So, you could actually simplify the problem by these kind of statements. If the flow is along or normal to the thermal gradient. So, what we mean by is as follows. This equation that you have written, so look at the terms u1 dou t by dou x1 plus u2 dou t by dou x2. Let us look at only the first two terms. Let us say that the temperature variation is allowed along the x2 direction, but it is only the u1 that is actually present, which means that both the terms will get dropped. Okay. That is the reason is that this will not be present and this will not be present. So, like that sometimes depending upon the velocity and the direction of the temperature gradient, you may actually have some of the terms on the advective term being dropped. Okay. So, when do these terms survive? When, for example, the velocity that you have specified and the gradient, they are aligning with each other. So, only when such situations, so along, so only then the term survives, otherwise they actually do not survive. Sometimes we may have viscous dissipation being present or not. So, if you say that the viscous dissipation is not present, that means that you can actually drop this term. Okay. Like this, even in a liquid domain, you may have the governing equation for temperature having less terms because of the assumptions that we make. So, using these problem statements, we start off first of all with the generalized Fourier heat conduction equation, then using these assumptions we reduce the number of terms, and then we have a simplified partial differential equation, which when we integrate and then using the boundary conditions as the integration constants, we then arrive at the solution of temperature as a function of distance. So, this is how we can arrive at the thermal profiles in a given problem. So, with this we close this session and then look at the practice problems for any numerical problems that you could work with in the course website.